Hello, welcome back to Elliptic Curves over local fields still. We are talking, last time we were talking about the action of inertia. So here is the setup where you have a local field, its algebraic closure, its maximal and ramified extension within the algebraic closure. And then last time we discussed a number of fields. There's decomposition groups and inertial subgroups. Once you pick a prime and a prime above a prime in the local field case, it's easier because there's only one prime at each level. And then the decomposition group is the entire Galois group. And the inertia subgroup is the piece that sits inside the decomposition group that acts trivially modulo the maximal ideal. So those elements that in fact induce the identity automorphism on the algebraic closure of the residue field. Oops. Okay, so we wanted to know how inertia acts on torsion points. And what we proved last time was this proposition. We proved that if you have an elliptic curve that has non-singular reduction, so we call that good reduction. So if there is good reduction, then if M is relatively prime to the characteristic of the residue field, then the M torsion is unramified. I didn't mean to circle it in green. I just circle it like this. The M torsion is unramified at nu. So what that means is that the points are fixed by inertia. And what that means is that if you adjoin to your base field, the coordinates of these points, since the points themselves have to be fixed point-wise by inertia, the extension that you get is unramified. So this is also telling you that the extension that you get when you just want to define the M torsion, so the extension that you get by adjoining M torsion points is unramified at nu. This will have consequences when we study, when we try to prove the Mordell-Weil theorem. And then if you take a prime then that is not the characteristic of your residue field, then you can do the Tate module. And the Tate module is also unramified. You can do also automorphisms of the Tate module that are induced from Galois. And this tells you that inertia just gives you the trivial automorphism. And again, it means that the field of definition of the Tate module is unramified at nu. So that if you were to put all the L torsion points in a tower and define an extension that is defined by all the coordinates of L torsion, power torsion points, that would be unramified at nu, as long as the characteristic is different from that of the residue field. So is there a converse to this statement? So this statement says that if it's good reduction, then we have unramifiedness. Is there a converse that if it is unramified, then it is good reduction? And it turns out there is. This is a deep theorem. I'm not going to prove here, but this is a very important result, which is called the criterion of neuron og, oops. Og and Shefarevich. And it says the following. It says that if you have an elliptic curve over a local field, the following are equivalent. So E has good reduction over K, meaning that the curve over the residue field is still an elliptic curve. This is equivalent to EM is unramified at nu for all integers M bigger or equal to 1, relatively prime to the characteristic of the residue field. C, the Tate module the elliptic Tate module TL of E is unramified at nu for some or all primes L relatively prime to P. Let's call that P, the characteristic of the residue field. And D, EM is unramified at nu for infinitely many integers M relatively prime to P. Okay, so it turns out that that being of good reduction is actually an if and only if to being unramified at nu for all integers M that are relatively prime to P, and in fact it's a little bit more flexible than that. If you have that the Tate module, for example, is unramified for some prime L relatively prime to P, then that already tells you that they have that you have good reduction over K. Okay, so there is that, and this is actually really useful also in knowing, for example, in the division field, this is going to tell us that if you have a division field, an M division field, the only places where this might be ramified is at places dividing M. All the other places that are not dividing M and places where there is the places where there is bad reduction and the places dividing M are those where there might be ramification. Everything else needs to be unramified. We'll come back to this during the proof of the Mordell-Weil theorem. Okay, so
sorry to interrupt.
Yeah.
So for this criterion, I think there are some generalization to a Bayesian variety that the same statement is true, right?
I believe so. Yeah.
Okay. I can probably check it myself.
Yeah, I would have to check, but I believe so. I believe it's yeah, the equivalent statement is true for abelian varieties.
Okay.
Yep.
Thank you.
Okay. So let's see. Let's move on to let's talk a bit more about good and bad reduction. So I just defined a moment ago what good means. We've been sort of like talking about it all the time. So remember that we have an elliptic curve, or a local field given by a minimum model. Okay, we can always pick a minimum model, and then we have reduction sends us to a curve over the residue field, and then we define the different types of things that can happen are the following. First, we say that E has good reduction, good or stable. We'll explain the meaning of stable here in a moment. A stable reduction over K if E twiddle is non-singular, so it is an elliptic curve itself. Okay. We say that E has multiplicative or semi-stable reduction over K if E twiddle has a node singularity. So remember that looks like a node looks something like this in the graph, although over a P or over a finite field, there is no such graph, but basically that's what it means. And then there are two cases in multiplicative reduction. If the slopes of the two lines, the two tangent lines that are at the singularity, so you see that here there are two slopes, there are two tangent lines at the singularity, and you can compute those and check what are the slopes there. So if the two slopes are in K, in little k, then we say that it is split multiplicative. And if the slopes are not in K, they are not in K, then it is a non-split multiplicative reduction. And part C is that you have additive reduction or unstable if E tilde has a cusp. In that case, the picture looks like this, and there is only one tangent line. It's not really a tangent line. It's not only one because the derivatives at that point completely vanish. So there is no well-defined tangent line. But if you were to define one as a limit, there would be only one such tangent line, and that's a cusp. We already saw sort of like what explains the terminology, why the terminology multiplicative and additive makes sense from long ago in chapter 3. So let me remind you in this language what that means. So here is a proposition bringing back the language of chapter 3, result 1.4, and chapter 3, result 2.5. So let EK be given by minimal Weierstrass equation, y squared plus a1xy plus the dot equals x cubed plus the dot, and let delta E be the minimal discriminant, and C4 of E be as usual. Okay, then remember that then E has good reduction over K, means that the reduction curve is non-singular. This means that the discriminant is non-zero. So non-zero when you reduce. So it must be a unit. So the valuation must be 0. Okay, of the discriminant. So i.e. the discriminant is a unit in the ring of integers. And in this case, the reduction is an elliptic curve itself. Okay. B, remember that one has multiplicative reduction when there is a node, but we knew when there are nodes is when the discriminant is 0, but the C4 is non-zero. So translated to reduction, this means that the valuation of the discriminant is greater than 0, so it reduces to 0 in the finite field or in the residue field, but the valuation of C4 is 0, so it doesn't reduce to 0. Okay, and in this case, remember also that we discussed that the non-singular points over K bar are isomorphic to the multiplicative structure of K bar. Okay, which that explains the terminology multiplicative. Oops. That explains, this notation explains the fact that this is isomorphic to the multiplicative structure of K bar explains multiplicative. By the way, so this was a proof that was left in the exercises. There is a new homework set in the website, so keep looking for more for new homework sets. I should be putting another one up soon also. And C, E has additive reduction when both the discriminant vanishes and the C4 vanishes, right? And in this case, what we have is that the reduction is isomorphic to the additive subgroup of K bar. Okay, which again justifies the notation additive. We will explain in a moment the other terminology that I used, that good is stable, multiplicative is semi-stable, and additive is unstable reduction. We will explain that in a moment, but let me give you some examples of reduction of elliptic curves. So for example, let's make this a little thinner. Yes. Let E1 be y squared equals x cubed plus 35x plus 5. Here, I have computed delta to be minus 2 to the 4 times 5 squared times 71 times 97. So it is a minimal model at all primes. Okay, so this is an elliptic curve over Q, but I'm going to consider it in over QP for every P. And C4 is minus 2 to the 4 times 3 times 5 times 7. So so E1 has good reduction at, for example, at P equals 7, right? Because P equals 7 does not give you, the delta is not 0 modulo 7. You get that E1, the reduction is y squared equals x cubed plus 5, which is over F7, is a perfectly fine elliptic curve. However, at 5, there is bad reduction. At 5, there is bad reduction. And since the discriminant and C4 vanish, mod 5, we have additive reduction. Okay, and you can see that in this case, the reduction is the curve y squared equals x cubed over f5, which is certainly a cusp. And if you want, what we're going to do is write this sort of as a Taylor expansion to look at like what are the tangent lines. So I'm going to write it like this, writing the entire Weierstrass equation as a Taylor expansion. And then what happens is that the line y equals 0, so this tells me that y equals 0 is the tangent line at 0, 0, where the singularity happens. Okay, we're going to do that in more general. So if you have an elliptic curve given by f of x y equals 0 and the singularity is at p x naught y naught is the singularity, then we have that the derivatives at p vanish, and therefore if I write my Taylor expansion of my polynomial at p, then that is going to be, you see the first derivatives vanish. So what that tells me is that the linear terms of the expansion vanish, and I get just quadratic and cubic terms in terms of x and y. So what happens is that the quadratic terms, you can factor it like I did so here, and that tells you what are the tangent lines at the singularity. So what we're going to do to analyze the singularity, in particular to analyze whether there is multiplicative split or non-split reduction, what you do is factor the quadratic term here, and it factors like follows: y minus y naught minus alpha x minus x naught times y minus y naught minus beta x minus x naught minus x naught cube. So this is, so again, this is a Taylor expansion of the polynomial, and these are the tangent lines. These are the tangent lines at the singularity. Okay, so let's go back to the example, and then you see that the prime, what prime do we have here that is interesting is I think I'm going to switch curve to look at some multiplicative reduction. So another example here is this one. So take E2 to be y squared equals x cubed minus x squared plus 35. And then delta here is minus 2 to the 4 times 5 times 7 times 941. You can clearly see that 5 and 7 are going to be bad because 5 and 7 divide there, but all of a sudden, like 941 comes out of nowhere as a bad prime. In any case, C4 is 16, so they are all primes of multiplicative reduction. So let's see what happens, for example, at p equals 5. At p equals 5, you have y squared. If I put all the terms on the left, like I did for the Taylor expansion, the 35 vanishes, so I get y squared plus x squared minus x cubed is congruent to 0 modulo 5, okay, over F5. And then you factor this and try to factor it over F5. And what do I get? I get y minus 2x, y plus 2x minus x cubed is congruent to 0. And then you see that because minus 1 is a square mod 5, I'm able to factor it, and then I have a split multiplicative reduction. So bad split multiplicative reduction at 5. Okay. For p equals 7, though, when I try to do the same, I also have the same equation, but now over F7, this does not factor because the square root of minus 1 is not, so minus 1 is not a square in F7, and therefore what you get is bad non-split multiplicative reduction at 7. And I will leave it up to you to figure out what happens at 941. Okay. Let's go yet to another example. Give that a second. Take a sip of coffee. Okay, so one more example, and that is going to move us towards explaining a stable versus unstable reduction. So now take E to be y squared equals x cubed plus 7 cubed. This elliptic curve has delta minus 2 to the 4 times 3 cubed times 7 to the 6. And C4 is 0. Okay, so in particular here, 7 has additive reduction. This is minimal at 7, but the reduction is additive because 7 divides delta and divides C4. Okay, so P equals 7 is bad additive. Okay, but you can see that I can't, this is minimal, but if I went up to adjoining the square root of 7, now 7 cubed is a 6th power over q adjoining the square root of 7. So what happens if I go and consider my elliptic curve, instead of over q, I'm going to consider it in an extension of q. And in this case, E is now y squared equals x cubed plus the square root of 7 to the 6th power. But now I know that I can do a change of variables to get rid of that square root of 7. So that now this is not minimal. At 7, not minimal at 7, or over the square root of 7, really. And we can do a change of variables by y prime is the square root of 7 cubed y, and x prime is the square root of 7 square x. And that brings me to a new model, which is this change of variables is rational over this quadratic extension of q. It brings me to a new model of the form, of this form, now over the square root of 7. And now this has good reduction. Has good reduction where at the prime ideal above 7 of q adjoining the square root of 7 above 7. Okay. So what happened is that I went from bad additive reduction to good reduction at the prime by going up in an extension. So this is why we say that additive reduction is unstable, in that you can go up by an extension and get rid of that additive reduction. However, good reduction stays stable on extensions, and multiplicative reduction is semi-stable in that you can go from non-split to split reduction. Okay, so we are going to define things in that vein. So let me increase this now to back to 2. So definition, E over K, let be an elliptic curve. We say that E has potential good reduction over K if there is a finite extension K prime over K such that E has good reduction over K prime. And that is the example that we just gave, that our original curve, so in the previous example, our original curve had bad reduction over Q7, let's say. So over the 7-adic field, there's bad reduction. But when I go to one ramified quadratic extension of Q7 adjoins the square root of 7, then I get good reduction in that extension. So this elliptic curve had potential good reduction over Q7. Not good reduction because the reduction was additive, but potential good reduction. Because so in the example above, E over Q7 given by y squared equals x cubed plus 7 cubed has potential good reduction, bad additive, and good reduction at the prime ideal square root of 7 of Q7 adjoint the square root of 7. So this would be my K prime field, and this is my K field. Okay? Okay. So now let me prove what I just sort of said, or state at least what I just said out loud, that about good reduction and bad reduction. So this is the semi-stable reduction theorem, and it says the following. So again, let E over K be an elliptic curve. Then first, if you have an unramified extension, so let K prime over K be an unramified extension of local fields. We're still in the territory of local fields. Then the reduction type of E over K, which is good, multiplicative, or additive, is the same as the reduction type of E over K prime. So if you want to change the reduction type, you're gonna have to work hard at it and use ramified extensions. So in an unramified extension, you're not going to get rid of bad reduction. It's going to stay the same reduction you had over the base field. Now, let K prime over K be any finite extension. If E has either good or multiplicative reduction over K, then it has the same reduction, the same type of reduction over K prime. Okay, so now under any finite extension, if you have good or multiplicative reduction, you are not going to be able to change it. It is still going to be good or multiplicative reduction. Okay. You might be able to go from non-split multiplicative to split multiplicative. That can change. Okay, so non-split multiplicative may become split multiplicative, but that's all that can happen. That's why it's saying like multiplicative will not change. It will maybe change from non-split to split, but that's it. You cannot go back. If you have split, you cannot go up to non-split though. And finally, there exists a finite extension K prime over K such that E over K prime has either good or split multiplicative reduction. Okay, so there is an extension where if you have additive reduction or if you have non-split multiplicative reduction, you're going to be able to go up to an extension where you either have good or a split multiplicative reduction. So that's why additive is unstable. You can always resolve it. Non-split, you can resolve to split, and good stays always good no matter where you go up in your extension. I'm not going to prove parts A and B, but I wanted to quickly discuss part C. How do you reach an extension where there is good or a split multiplicative reduction? So here's proof of C, even though it looks like an A. Proof of C. Great. So again, I want to go from an elliptic curve EK to an elliptic curve over K prime with good or a split multiplicative reduction. Okay, that's what the proof says. And let's assume that the characteristic of the residue field is not 2 for simplicity. And the first step is that I can extend. Okay, so I'm allowing going up to a finite extension. So you can extend, you can always extend K by a finite extension. Such that E can be given by a model of this form. You can always extend, so it's now of this form, x minus 1, x minus lambda. Okay, this is what's called a Legendre normal form. Okay. And by the way, this finite extension is not very mysterious. This is in the book in chapter 3. Silverman explains why this holds. So basically, the finite extension is either k adjoint the 2 torsion of your elliptic curve, or a quadratic extension of k adjoint the 2 torsion points. Okay, so definitely that's a finite extension, and you can get there. Once you have a normal Legendre normal form, it turns out that this is a nice form to work with, because the C4 is precisely 16 times lambda squared minus lambda plus 1, and delta is 16 times lambda squared times lambda minus 1 squared. Okay, so so now there's going to be 3 cases. So here is case 1. If lambda, so the case 1 is lambda is an integer in your local field, and lambda is not 0 or 1 modulo the maximal ideal. This is already, k has been replaced by k. So this R is the ring of integers over a new extension where there is this model, okay? And in this case, what do we have? If lambda is not 0 or 1, and the characteristic is not 2, then you see that lambda, the discriminant delta, is non-zero modulo the maximal ideal. So the discriminant is actually a unit. Okay, so we already have good reduction, and we are there. Okay, great. So that case is already, the model already has good reduction. The second case is if lambda is an integer, but then lambda is either 0 or 1 mod m, then what happens, you can look at the discriminant. Now the discriminant is definitely 0, so there is bad reduction. But C4, if lambda is 0, what do I have? Z4 is 16, which is non-zero because the characteristic is not 2. If lambda is 1, I still have 16. Okay, C4 is congruent to 16 modulo m, which is non-zero, and therefore I have the reduction is multiplicative. If it is non-split, the slopes are now in if it's non-split, the slopes are not in the base field k. However, the slopes are defined by a quadratic polynomial, so I can go up by a quadratic extension if needed to adjoin the slopes. And then after possibly a quadratic extension, reduction is split multiplicative. I just need to adjoin. So in here, possibly a quadratic extension, you just have to adjoin to k, adjoined alpha, beta, the roots. If you adjoin 1, you actually have adjoined both, but in any case, you adjoin those slopes, and that's a quadratic extension. Okay, and we are at split multiplicative, so that's good. And then there is case 3, which is the case that lambda is not integral. Okay, but if it is not integral, then I can multiply something to kill the denominators. So choose r such that pi, the uniformizer of r, is pi r times lambda is a unit, then what happens? Then I'm going to change variables. I'm going to write new variables, x prime and y prime. I'm adjoining and change k prime. So this change of variables is in the field. I'm going to have to adjoin a square root of pi, so go up by a quadratic ramified extension, and this gives an elliptic curve now over a model for our elliptic curve that is of the form y prime square equals x prime minus pi to the r x prime minus pi to the r lambda. Okay, but now in this case, you can check that now delta, the new delta is in the maximal ideal, but C4 is a unit. So it has a split multiplicative reduction. You can achieve a split multiplicative reduction once you resolve the once you add the slopes. Okay, so that gives me what I wanted, that by going into a Legendre normal form, I'm almost there, either good reduction or pretty close to multiplicative reduction. Okay, let me stop here, and then I'll continue with the last section of this on local fields, which is the quotient of E by E naught.